Graph theory is one of the most important topics in computer science, with many applications in fields such as mapping and social networking. Having a solid grasp of how to represent and use them is crucial for success in the later divisions of USACO. Let's begin by considering a map with several towns connected by a network of roads. By using a graph to represent this scenario, we can answer a variety of questions that might otherwise be difficult to answer in a systematic fashion. For example, given two towns, Town A and Town B, we would be able to use graphs to find the shortest distance needed to travel from Town A to Town B by road. Before we proceed any further, let us first get some basic definitions and terminology out of the way, starting with a proper definition of what a graph is. A graph consists of a series of nodes and edges, where nodes are connected by edges. In our previous example, we had a map of towns connected by roads. Using a graph, we would represent each town as a node and each edge as a road. Just as roads may vary in length, edges too may vary in weight. A weighted graph is a graph in which each edge is given a particular weight. Likewise, an unweighted graph is a graph in which edges are not given a weight. Edges can be directed, meaning they can only be traversed in one direction, or undirected, which means that they can be traversed in either direction. A directed graph is a graph with directed edges, whereas an undirected graph is a graph with undirected edges. A node A is said to be connected to another node B if it is possible to go from A to B by traversing a sequence of edges. A connected component is a subset of nodes which are connected to each other. There's loads more terminology in graph theory, but for the sake of simplicity and to keep this video from dragging forever, we won't delve any deeper into it. If you're interested, a more complete list of graph theory terminology can be found on our website. With that out of the way, we can now discuss various ways to represent a graph. The simplest and perhaps most intuitive way is to use an adjacency matrix. Suppose we are given the following directed graph, with nodes numbered from 0 to 6. We can use a 5x5 or 6x6 matrix to represent the edges on the graph. For instance, the directed edge from 0 to 2 is represented by a 1 in row 0, column 2 of the adjacency matrix. In general, a directed edge from node I to node j can be represented by inserting a 1 in row I, column j of the adjacency matrix. If no edge exists between two nodes, then a 0 is inserted instead. In our previous example, the graph was directed, so each edge has a unique corresponding entry in the matrix. You might be wondering how we might use an adjacency matrix to represent an undirected graph. Rather than having each edge corresponding to one entry in the array, each undirected edge would have two corresponding entries in the adjacency matrix, one for both directions. For example, the edge between nodes 0 and 2 in the following graph would correspond to these two entries on the adjacency matrix. Notice how the matrix here is symmetrical across the diagonal. This is the case for every undirected graph. This method of representing a graph has many advantages. For one, we can easily check if a specific edge exists in constant time by accessing its corresponding entry on the array. Adding and deleting edges can also be done in constant time. If a graph is dense, meaning it has a large number of edges, then this method is suitable for storing all the data efficiently. The main caveat with using an adjacency matrix, however, lies in the fact that it isn't very space efficient. We always need an n by n matrix to represent a graph, even if it is sparse or doesn't have many edges. Furthermore, checking the neighbors of a given node, the nodes that are incident to or share the same edge with it, requires scanning an entire row of the matrix. For searching algorithms such as DFS and BFS, which constantly require finding neighbors of a node, this inefficiency simply isn't doable. Thus, while there are a few algorithms that are easier to implement using an adjacency matrix, we would need an alternative graph representation in order to implement DFS and BFS properly. This is where adjacency lists come in. Adjacency lists allow easy access to a node's neighbors by storing the neighbors of each node on the graph in a list. Here's how they work in an undirected graph. If we have n nodes, then for each node we simply keep a list of all its neighbors. This is enough to store all the edges and vertices of a graph. For example, in the following graph, node 0 shares an edge with nodes 2, 4, and 5. As you can see, the corresponding adjacency list for node 0 reflects this information. In the case of a directed graph, we only store the outgoing neighbors of a node in its corresponding adjacency list. As you might have guessed from the name, the outgoing neighbors are the neighbors which share an edge directed away from the starting node. For instance, in the following directed graph, the outgoing neighbors of node 0 are nodes 2 and 5, and this is represented in its corresponding adjacency list. We previously mentioned that adjacency lists make finding the neighbors of a given node incredibly easy, since that merely requires checking the node's list. Adding edges is also relatively easy. It can be done by simply appending a neighbor in the corresponding list. Additionally, the space used is dependent on the number of edges in the graph, making it ideal for sparse graphs. However, the adjacency list's representation does have its own downsides. Unlike with an adjacency matrix, edge lookup is incredibly slow. In the worst case, it might be necessary to traverse all the neighbors in a node's list. Removing an edge is just as slow. Even so, adjacency lists are incredibly useful and oftentimes recommended for most typical graph searching algorithms. Now that we've gone over how graphs work, let's try using them in a problem. If you would like to try solving the problem on your own first, make sure to pause the video. Here's what the problem asks. In X country, there are n cities numbered 0 to n-1. There is a network of one-way roads connecting the cities. A pair of cities are connected if there is a one-way road directly to and from both cities. For each city, print out the number of cities that they are connected to. If we look at the sample input, the number of cities is 4 and the number of one-way roads is 6. Cities 0 and 3 are connected to each other because there is a one-sided road between both of them. Cities 2 and 3 are also connected for the same reasons. Thus, cities 0 and 2 are both only connected to one other city, city 3 is connected to 2 other cities, and city 1 is not connected to any other city. Note that the problem states that cities are connected by a series of one-sided roads. This tells us that we want to create a directed graph. To solve this problem, we can either represent a graph using either an adjacency matrix or an adjacency list. Let's cover how we would solve this using a matrix. If we were to create an adjacency matrix for the sample input, we would have the following matrix. The 1 in row 0, column 3 represents a one-sided road from city 0 to city 3. To begin, we create an empty n by n matrix which we can then populate using the input data. Then, for each row of the adjacency matrix, we would iterate through each of the columns until we reach an entry with a 1 in it. This tells us that the city corresponding to the row may be connected to the city corresponding to the column. A simple check can confirm if this is really the case. For instance, if row I column j has a 1 in it, we can check if row j column I also has a 1. This can be done in constant time. And if it does, then we would add 1 to the number of connected cities for that row. After iterating through the entire row like this, we can print out the final count and repeat the same process for the remaining rows. That's it for our intro to graphs. Hopefully it wasn't too confusing. If you enjoyed our content, don't forget to like, comment, and subscribe.